It's my great pleasure and great honor to introduce Zoubin Ghahramani. Zoubin is a joint invited speaker between the Innovative Applications of AI conference and AAAI, and we are really fortunate to have been able to attract him here. Zoubin is a professor of information engineering at the University of Cambridge, and he's also a chief scientist at Uber, combining the two in doing very interesting things. He's a deputy director of the Center for the Future of Intelligence. He's also a fellow of St. John's College and a founding director of the Alan Turing Institute, which is the National Institute of Data Science in the UK. He co-founded Geometric Intelligence, which is now Uber AI Lab, which he is running. And he's also an elected fellow of the Royal Society in the UK for his contribution to machine learning. He has worked in many, many areas of AI, and I'll mention a couple of them, but there are many others that I won't be able to touch upon. They include variational methods for approximate Bayesian inference, graphical models, computational neuroscience, and obviously statistical machine learning. So I hope you can join me in welcoming Zoubin Ghahramani for this invited talk. Thank you very much.
Thank you. It's a great pleasure to be here at this joint talk for the two conferences. Okay, so I'm going to be talking about probabilistic machine learning and AI. And I'm just going to start out by saying it's an incredibly exciting time for AI and machine learning. I'm sure you are all aware of this. We've had many recent breakthroughs in AI and games. For example, Atari, Go, poker, new breakthroughs in chess. But maybe even more importantly, we've had an era of really interesting applications of AI and machine learning. So on this slide, I just have 6 things I could fit in. We could have fit many, many more. But areas like speech and language technologies, computer vision, many fields of scientific data analysis, all the recommender systems that we all interact with, the very exciting future for self-driving cars, applications in finance, automated trading, and many, many more things we could have fit on this slide. So it's a hugely exciting time. And when we think about this mission of AI, one of the questions that comes to mind is like, where are we? How far are we from what we need? Do we have all the principles that we need to be able to solve the challenging problems? Do we have the sort of practical tools that we need? And clearly, to solve some of these challenging AI problems, we need principles for perception, for learning, for reasoning, and for decision making, and probably a few other things I haven't left, but certainly for I haven't put on this slide, but certainly those 4 are very important things to think about. And I'm going to try to return to this at the end of my talk. So are we there with the principles that we need to build AI systems? So think about it, maybe. Who thinks, by the way, who thinks we have the principles we need? Raise your hand if you think we have everything we need to solve AI. Who thinks we're missing something? Okay. All right, so we'll return to this. Okay, so, one of the things that the sort of like 1,100-pound gorilla in the room is deep learning, right? So, one of the things that people often think these days, especially people who haven't been in the field of AI for very long, is that deep learning is going to solve everything. So deep learning is, the tool that is going to allow us to create intelligent systems and solve all of our problems. So let's talk about that for a little bit. Just to set the stage, many of you, I'm sure, know this, but what are deep learning systems? So fundamentally, deep learning systems are neural networks, and neural networks are tunable nonlinear functions with many parameters. That's basically all they are. Okay, and the parameters in a neural network, we could call them theta. These are the weights of the neural network, and neural networks are particularly interesting functions because they're nonlinear generally in both the inputs x and the parameters theta. So what I've shown here is, if you can see, I don't know if you can see my pointer, what I've shown here is the simplest possible neural network which takes a linear combination of the inputs and passes them through a nonlinearity, a sigmoid nonlinearity, like a logistic or something like that. That's probably 70 or 80 years old. And what modern neural networks do, which is a little bit more interesting, is they represent this function from the inputs x to the outputs y via a composition of functions. So that's the sort of layers in a neural network. So here is a 2-layer version of a composition of functions. And so what do you do with these neural networks? Well, you train them generally by maximizing likelihood. So almost every loss function that's used to train a neural network corresponds to a likelihood of some kind. Not everyone, but almost everyone, or a penalized likelihood of some kind. And you generally train them with some stochastic gradient procedure. So at the bottom, the core of a neural network is just a nonlinear function with a little bit of basic statistics and a little bit of like elementary optimization thrown together. And it's incredible how powerful these things have been in the modern era. But let's not forget that that's all that's going on in most neural networks. Okay, so the field of neural networks, which really got me excited about being an AI researcher in the mid-'80s when I first started, that's what I got really excited about, has basically been rebranded as deep learning recently. And deep learning systems, sort of modern deep learning systems, are very similar to the things that were popular in the 80s and 90s, with a few very important changes. So first of all, we've had some new ideas. The field has had some new ideas and new innovations, like making us able to learn systems with many layers, using different kinds of nonlinearities like ReLUs, different forms of regularization like dropout, and architectures for recurrence like LSTMs, GRUs, etc. So there's some new ideas in there. But really importantly, we now have vastly larger data sets, web-scale data sets than we had in the 1980s. So when I was, again, as a personal anecdote, the first major thing that got me excited about machine learning was my undergraduate project, which was learning how to parse English using a recurrent neural network. This is in 1986. The problem was, our computers were incredibly slow. Even the connection machine, a highly parallel computer I was trying to program, was very slow. And my data set was tiny. In hindsight, this was doomed to failure. And of course, it failed. I didn't, get a good parser that was competitive with the existing symbolic parsers back then. So we have vastly larger data sets. We have vastly larger compute resources, GPUs on the cloud, new hardware architectures. We have much better software tools that makes it much easier to actually build these neural networks. And we have, because of all these things, we also have vastly increased industry investment and also media hype. And the good thing about that is that more people are coming in. When you get an order of magnitude more people coming into the field, your progress speeds up. So there's been tremendous progress, and we've achieved a lot of really interesting breakthroughs with deep learning systems. And I don't want to minimize from that, because I think that is really important for the AI endeavor. But these systems also have limitations. So although these systems have given amazing performance on many benchmark tasks, they're also generally very data hungry, often needing millions of examples. They're very compute intensive to train and deploy. They're poor at representing uncertainty. This is something I'm going to come back to because it's sort of a great interest of mine. It's non-trivial in neural networks and other deep learning architectures to incorporate good prior knowledge to handle symbolic representations. Of course, all of these things are things that many people are working on. So I'm not saying that these are insurmountable, but these are things that are at the boundaries of what we can do with neural nets right now. Neural nets are famously easily fooled by adversarial examples. So you can perturb a few pixels in an image and get the neural net to give you confidently wrong answers. They're finicky to optimize. So non-convex, you know, finding the choice of architectures, how to initialize them and so on. All of this is black art. And they are generally uninterpretable black boxes. They're lacking in transparency. They're difficult to trust. And that makes them hard to deploy on some really important problems. So these are the challenges in the field of deep learning right now. And I think this is where a lot of the interesting stuff is going on in trying to overcome these challenges. But what I want to talk about for most of my talk is kind of what's next. So deep learning has clearly been a revolution in the field. We can all agree on that. And now we can move on, because we're researchers. We want to see what is next. And I'm going to give a very personal answer to what I think is next. And the personal answer really comes from a particular worldview that I and, you know, of course, many of my colleagues have about what machine learning is. So the way I'd like to think of machine learning is in terms of probabilistic modeling. And the point of that is that in many fields of science and engineering, what we're really interested in is building models, okay? And what's a model? A model describes data that one could observe from a system. Okay, that's the way you tell whether your model is good or not. And it doesn't have to be a model of all the variables. It doesn't have to be a generative model of everything. It could be a model of the outputs given the inputs, but that's still a model, okay? Almost everything out there that's machine learning is a model of some kind, okay? And now what we're going to do is we're going to use the mathematics of modeling. And there is a good language for dealing with models, and that is the language of probability theory. Because fundamentally, if you have a data set and you want to model something about the world, if you want to predict something about data you haven't observed yet, any sensible model would have to capture uncertainty, okay? Because how else are you going to make predictions? And probability theory is the mathematical language for dealing with uncertainty. Just like calculus is the language for dealing with rates of change, probability theory is the language for uncertainty. So we're going to use probability theory for all forms of uncertainty in our model, all aspects of noise, all things that we don't know for sure. And then we're going to continue using probability theory in the form of what's called inverse probability or Bayesian inference, and that allows us to infer unknown quantities, adapt our models, make predictions, and learn from data. So it's a very, very simple framework, and many, many machine learning problems fall into this framework, or at least should fall into this framework. So, where, you know, in equations, what is this all about? And of course, I know many of you know this, but let me explain Bayes' rule the way I see it. So Bayes' rule is this rule here, which is telling us how to update our knowledge or beliefs about things we don't know, which I'm going to call hypotheses, from things that we do know or measure, which I'm going to call data. So in a Bayesian's world, there are only two kinds of things out there: the stuff that you measure and everything else. And the stuff that you measure is the data, whether it's the perceptual data for a robot or some medical data that you measure, whatever it is. And the stuff that you don't know, that's uncertain. And we need to represent our uncertainty about that. And we're going to use probability distributions to represent that uncertainty. So before we've observed the data, we have the prior, that's this P of hypotheses here. Then for any hypothesis, we need to be able to evaluate how probable is the observed data under that hypothesis. That's the familiar likelihood. And when we multiply these two and we renormalize, summing over all plausible hypotheses we're willing to consider, what we get is the posterior distribution over the unknown stuff, the hypotheses given the data. And that is sort of a simple universal rule for updating beliefs in light of data. It's a rule that tells us how to do learning. Learning is fundamentally the transfer from prior knowledge to posterior knowledge. If I get more data, I just apply the rule again to my current state of beliefs to get a new posterior thing. There's nothing special about that initial prior. And that's the basic framework. And now if we apply this to machine learning, what we get is the following, basically, 3 equations defining learning, prediction, and model comparison. One thing I want to point out is that Bayes' rule itself is even not really an axiom. It's just a corollary of 2 simpler rules in probability theory, which are the sum rule and the product rule, written at the top. So everything basically follows from the sum rule and the product rule. And any time you deviate from that, you need to explain why. Is it because you don't believe in probability theory? Is it because it's computationally infeasible? There must be a good reason in the Bayesian framework. So learning, if we now take Bayes' rule and we substitute in theta for the parameters of our model, is basically the process of updating from our prior over the parameters, our state of belief before observing the data, through the likelihood, multiplying in the likelihood, and then renormalizing, and then we get the posterior of the parameters, which represents plausible settings of these parameters given the data. Prediction, any quantity we might want to predict, call it x, given the data d. Well, Bayes' rule, the sum rule, and the product rule tell us that to make a prediction, what we need to do is average or integrate the predictions of all possible parameters weighted by the posterior that we computed over here, the term in green. So it's a natural ensembling process, the process of prediction. And if I want to compare 2 different models, then I apply Bayes' rule at the level of models M. Okay? So M are sort of, model structures I might want to consider. And this is a very powerful idea. We can use it to do all sorts of model selection, model comparison, ensembling, etc. So that's it. That's Bayesian machine learning in one slide. And, in some way, we don't really need much more. But maybe we should ask ourselves, why do we need these probabilities in the era where deep learning has been so successful or seemingly successful without most deep learning papers starting out by saying, here's Bayes' rule and everything follows from that? Well, should we throw away probabilities? Should we just move on and say, well, that's old, that's like from the 1700s. We're in the 21st century now. We don't need that. So do we need that? When do we need probabilities? And I would argue that they really do matter for AI. So here's a few examples of places where I think probabilities really matter for AI. We'd like systems that have calibrated uncertainties, model and prediction uncertainties. And the reason for that is that we want systems that know when they don't know. Okay? If we're building a self-driving car with a pedestrian detector, then we would like it if the conditions are weird, if like the sensors fail or it's foggy or it's a pedestrian that looks somewhat unusual. We want it to say, I don't know. We don't want it to confidently give us the wrong answer, like most current perceptual systems do. The probabilistic framework also allows us to do very elegant model complexity control and structure learning. So actually, we don't need regularization. Regularization and overfitting, these are not Bayesian problems. These are hacks for solving the thing that probability theory solves naturally. I mean, that might sound a bit harsh, but from a purist Bayesian point of view, these are, let's call them approximations to actually computing things with the sum and product rule. For AI, we clearly want to build systems that make rational decisions. So now if we think about like what are the principles whereby rational decision making come in, well, I'll talk about this a little bit more in a couple of slides, but we want systems that update the beliefs in light of data in a coherent manner, and then make decisions that maximize some utility or minimize some loss in an expected sort of way, which is what you would imagine from utility theory. We need systems where we can build in prior knowledge into our learning, not just like deploy black boxes, because sometimes we have prior knowledge and we want AI systems that can incorporate that. And not just that, but they need to update their knowledge in light of data in a coherent and robust way. And we want to make sure our learning systems work not just with big data sets, but also with small data sets, because a lot of challenging AI problems involve making the right inferences from small amounts of data. So let me talk about sort of some of the foundations, some of the probabilistic foundations of where AI fits in, where probability theory fits into AI. Okay. So let's talk about the problem of representing beliefs in an AI system. So imagine you have a robot, and in order to behave intelligently, we think that the robot should be able to represent beliefs about propositions in the world, like, you know, my charging station is at this location, or this stormtrooper is hostile, or whatever the robot wants to believe, okay? And what we want to do is, in the brain of this robot, we want to be able to represent these beliefs numerically somehow, okay? And now we want to know, well, what is the mathematical language we should use to manipulate these beliefs, okay? So this is an interesting thing to think about, and this is something that, you know, has been thought about, like, at least from the 1940s. So here's the mathematics we're going to use. We're going to use the idea that B of x is going to represent the strength of belief of the system, or the plausibility of some proposition x, okay? So we're going to say, okay, B of x, this number is going to be between 0 and 1. 0 means that the system believes that x is impossible. 1 means that it's definitely true. So logic is at the extremes of this interval. And furthermore, B of x given y is going to represent the belief that x is true, given that we know that y is true. Okay? So we're going to use this B to represent things. And then in 1946, Cox wrote down some axioms, which were axioms about how to represent beliefs. For example, these are things like, we're going to use real numbers to represent beliefs, real numbers between 0 and 1. We want them to qualitatively correspond with common sense, and so there was a few sub-clauses there on what common sense would mean. And we want the systems that represent and manipulate beliefs to be consistent in a certain way. So if a conclusion can be reasoned several ways, then each way should lead to the same belief state. So if I have a couple of bits of evidence and I incorporate them in different orders, the belief state should not depend on the arbitrary order in which I incorporated that evidence. The robot or system must take into account all relevant evidence, so it can't just say, I'm going to flip a coin and I'm going to ignore this particular y that I observed at random, because that's sort of arbitrary, that's not rational. And then equivalent states of knowledge should be represented by equivalent plausibility assignments, equivalent numbers. So these are the Cox axioms, and then the consequence of these axioms is that these belief functions that I've written with B must satisfy the rules of probability theory, including the sum rule and the product rule and therefore Bayes' rule. So this is the alternative derivation of probability theory. This is not probability theory from the point of view of repeatable experiments and frequencies and so on that you get in classical statistics. It doesn't even involve, like, you know, measure theory and stuff like that. This is just about representing beliefs. And this is a representation of probability theory that I think is very relevant for thinking about AI problems. Here's another argument for why beliefs are important. And this is an argument that comes from kind of decision theory or games. And here is the question. Here what we have is the question of how do we use beliefs to make decisions about things that we're willing to bet on. So assume you're willing to accept bets with odds proportional to the strength of your beliefs. That is, if B of x is 0.1, that implies that you'll accept a bet where if x is true, you win $9 or say $10, more than $9. If x is false, you lose $1. So it would be rational, if you're willing to bet and that B of x is 0.1, that you would accept that bet. Then, unless your beliefs satisfy the rules of probability theory, including Bayes' rule, then there exists a set of simultaneous bets that you would accept. That set of simultaneous bets is called a Dutch book, that you're willing to accept, for which you are guaranteed to lose money no matter what the outcome. Okay? That's not about whether your beliefs are correct or not. We're not saying your beliefs have to be right. They just have to be coherent. And the way in which beliefs are coherent is they satisfy the rules of probability theory. So if we want to build rational agents that represent beliefs, and we want them not to be fooled by nature or by other more rational agents, then they better have probability theory at their core of their beliefs. Okay, so that's a bit of like the sort of philosophical almost background of probability theory. Now, as was mentioned, I'm heading up Uber's AI research lab, and one of the things that's very interesting about working on some of the problems that we're working on is that probabilistic modeling is actually really at the core of many of the most challenging things that we do. So many aspects of learning and intelligence depend crucially on representing uncertainty. And if we're looking at the modeling and prediction of the supply of drivers and the demand of riders over space and time, if we're trying to model cities and traffic and the complex dynamics of these things, if we're trying to predict the ETAs or do rational experiment designs, good pricing schemes, good causal inference, financial forecasting, self-driving cars, I'll mention that because people think that's the thing that we're working on. I mean, we have lots of people working on that, but there's everything else that a big technology company like Uber that's out there in the real world dealing with people in cities has to do. And believe me, probabilistic modeling is really central to what we do. We, of course, use deep learning. We have lots of functions we want to learn, and we have lots of data to learn those functions. So we use deep learning to do that, but it's really important to have those probabilistic models to be able to build a rational decision-making agent. And our CEO, Dara, to quote him, said the following: Uber is a giant machine intelligence problem. And it's a particularly challenging problem because we're trying to optimize and navigate the real world with all the uncertainty that that brings. So let me talk about some of the most, to me, the most exciting areas of probabilistic machine learning. And these are, of course, this is a very personal view. These are areas that I've been investing in and my colleagues and I have been working on. And to do this, I'll give you a map. Somebody asked me a couple of years ago to present my research program in one slide. So I had to come up with one slide to capture everything that I'm interested in. And it was a good exercise because it turned out everything, a lot of the things that I work on are related to a central mission, which is automating machine learning. And what I mean by that is that machine learning systems are not very rational right now. They're quite ad hoc. And in many places, we can make them much better, much more efficient, much more automatic. And I'm not going to talk about all of these things, but I'll try to give you three vignettes, three interesting areas that I think are very promising from here. So the first one I'm going to talk about is Bayesian deep learning. So remember, I was sort of almost juxtaposing deep learning and Bayesian as being in opposition, but they're not, actually. They're talking about different things. Deep learning is talking really about types of models, and Bayesian inference is talking about methods for learning, okay? So we can mix and match these two. And there's actually a deep and rich history of interesting work in this area. So let me motivate a little bit what I mean by this. So in a neural network or any other deep learning architecture, we have parameters. We have a function mapping from x to y, let's say. And we have some parameters. These are the weights. And if I wanted to be really Bayesian about my neural network, then I would need to capture things like not just the parameter uncertainty, right? Not just a single point estimate, but uncertainty in all of these weights or parameters, but also the structural uncertainty, like how many layers should I have? What should the layers look like? That's really computationally quite beyond hope, I think, right now. But formally, that's what we would have to actually capture. Let's talk about parameter uncertainty, because that may be closer to tractable. So here's a neural network. It's the same neural network as before. It has the same structure, same weights, whatever neural network it is. Doesn't matter. I've shown a very simple one here. And now we're going to treat this with a Bayesian lens. So the Bayesian lens would say there are parameters, theta, and these are the weights in the neural network. Before observing the data, I have a prior. That's P of theta given alpha. Alpha might be some hyperparameters. You can ask me where to set those from, but that's not as hard as people think. So you have a prior, and then after observing the data, you have a posterior, basically. That represents the distribution of parameters of your neural network that are consistent with the data. Now, something interesting that Radford Neal showed in 1994, in the previous sort of heyday of neural networks, is that a neural network with one hidden layer, if you treat it in a Bayesian manner in this way, and you take the limit as the number of hidden units goes to infinity of that model, then that converges to something well known in statistics called the Gaussian process, about a 100-year-old model. So actually what happened in the mid-90s is there were lots of people excited about neural networks, but they were frustrated that they were so hard to train and they had so many local optima and they weren't really producing great results back then. And they got excited. So part of the field got excited by support vector machines because they solve problems elegantly using convex optimization. And then the Bayesian part of the field said, well, why deal with these annoying finite neural networks when an infinite neural network can be handled with linear algebra using Gaussian processes? So they threw away neural networks and they worked on Gaussian processes. Now it turns out, to quote David Mackay, another pioneer in this field, that we may have thrown the baby out with the bathwater, if you've heard that expression. And it's probably good to revisit that. But we've recently revisited this theoretical result, and we've generalized it in this iClear paper to look at wide and deep neural networks. So this was just with one hidden layer. And it turns out that even for deep networks, if they're wide, when you take the limit, it's just a Gaussian process. And many of the models that were analyzed in the Bayesian neural network community, it turns out, are indistinguishable from Gaussian processes, which are much, much easier to deal with. So it's sort of an interesting curiosity, if you would say. Now, I haven't explained what Gaussian processes are. I could talk about that for an hour, but we don't have an hour. I would recommend people looking at that. They're very, very nice models for functions. Okay, so as I mentioned, the field of Bayesian deep learning has actually been around for a long time, and it can be implemented in many ways. So the key computational problem is doing inference over the parameters, coming up with the probability distribution of the parameters given the data for a neural network. And in the early 90s, actually Jan LeCun had a paper which did some Bayesian deep learning, but this was before, more from a physics perspective, before it was actually even recognized that that was Bayesian deep learning. Then David Mackay, Radford Neal, Jeff Hinton developed Laplace variational MCMC methods. Then there was a bit of a lull when everybody else kind of decided not to work on neural networks. And then early in 2011 and later on, many people have started to revisit inference methods for neural networks, trying to make Bayesian inference fast and cheap so that it's competitive with optimization. And this figure here is meant to show why we might care. So this figure shows a neural network fit to some data, trying to fit some function. That's all fine where you have the data, these black dots. But the point is, outside of where you have the data, what you'd really like is these big error bars. You'd like uncertainty to be well represented. And Bayesian neural networks will generally do that much better than a point estimate. We had a couple of very successful NIPS workshops, 2016 and 2017, and the videos of that are online if you're interested. So a very recent piece of work I want to talk about is how to combine deep learning with Gaussian processes. And this is not, the idea itself is not necessarily new, but one of the things that's interesting is that we can now do this in a very scalable way. So you can take a neural network and you can slap a Gaussian process on top at the end. This is a Gaussian process deep neural network, GPDNN. And then you can train the whole thing in TensorFlow using something that my group and others developed called GPFlow. So end-to-end training of the whole thing. So what's the point of that? Well, the point of that is that we're trying to have our cake and eat it too. We want to have the representational power of a deep neural network, but the uncertainty, the nice uncertainty properties of a Gaussian process. And this is one way we might be able to do that. And what we found is that we get more robustness to adversarial examples, and we get systems that generally are better at saying when they don't know. Okay, better extrapolation, better representations of uncertainty. So here's a picture that's meant to represent that. I'm going to show, let's look at this example here. This is a very toy example. If you can see, there's some orange dots and some blue dots. That's the training data. It's a simple classification problem in 2D. And the neural network, this is a neural network, the neural network can beautifully classify this data set. Okay? That's fine. You get very good training and test accuracy if you only test on this distribution. Now the question is, what happens when you go far away? What happens when you go all the way over here, all the way over here? And here is what the neural network will do. It will confidently, generally, it will confidently extrapolate to places where it's never seen data. It'll say the probability of being orange is 1, virtually 1 here, and it's virtually 1 here. Okay? That's bad. That's a system that doesn't know when it doesn't know. It should say, I don't know, way out here, because it's never observed any data way out here. This is a trivial example, but in high dimensions, this is going to happen, and you're not even going to know it. This is what a Gaussian process can do. Now, you can do a Gaussian process exactly in this small data, low-dimensional problem, and it performs as you would expect. It classifies the data really well, and then outside of the areas where it's seen anything, it reverts to white. White is, I don't know. It's like 0.5, okay? So that's the behavior that you want. This is the Gaussian process deep neural network. This is one particular run. The deep network has idiosyncrasies. When you run it on different runs, it will produce slightly different shapes. But essentially, it still classifies the data well, and it has a lot more regions out here that are in the I don't know area, or that are basically saying probability 0.5. And if you simply average this over 2 or 3 runs, you get something that looks basically like this. Okay? Okay, so that's just an illustration of one way of combining Gaussian processes and deep learning. I'm going to talk very briefly about 2 other ideas, and then I want to take some time for questions. So the second really exciting idea I want to talk about is probabilistic programming. So raise your hand if you have worked with a probabilistic programming system. Okay. Raise your hand if you know what it is. Okay, a larger fraction of people know what it is. Okay, well, even for those who know what it is, I won't spend too many slides on this. So one of the problems with this probabilistic modeling framework is that writing down probabilistic models and deriving inference algorithms is very time-consuming and error-prone. Okay? Now, the solution to that is to provide better tools, right? Just like happened in the neural net community. Once you have tools for automatic differentiation, it's a revolution. You can just write down the model, and the computer does the differentiation for you, right? You don't have to take derivatives by hand every time for every model. We want to do the same thing for probabilistic modeling. And so that's the solution is in the form of probabilistic programming languages. And these are languages for expressing probabilistic models as computer programs that generate data. In other words, simulators. Simulators are an idea that many fields have discovered and make use of all the time. So we're going to treat a simulator as a model. And it doesn't have to be, again, to be clear, it doesn't have to simulate everything. It doesn't have to be a generative model for everything. It could just simulate y as a function of x for whatever complicated y you have and whatever complicated x you have. Now, that's not the magic. The magic is that given a general purpose probabilistic programming language, we can develop universal inference engines. These are languages that do inference over over program executions, given the observed data. So intuitively, I have a simulator. From that simulator, I can simulate some fake data. And the process of learning is now I have some real data. And now I want to figure out how do I get my simulator to generate data that looks more like my real data. Now, in the optimization framework, what you do is you take derivatives through everything and you try to optimize the simulator to fit the real data. That's what maximum likelihood is. In the probabilistic programming framework, you say, my simulator has many parameters that are uncertain. What I really want to do is Bayes rule, given the observed data, on my computer program. Essentially running Bayes rule, which is running my computer program in reverse to infer what those random variables were given the data. There are many examples of this. Bugs, infer.net, etc. There are two projects I've been involved in. Turing, which is a probabilistic programming language based on Julia, and Pyro, which I'll talk about, which is a language developed at Uber AI Labs. And under the hood, there are many different inference engines based on Markov chain Monte Carlo and particle filtering and other methods. So here is like a typical model, a hidden Markov model written in one of these probabilistic programming languages, Turing. And it's just a few lines of code, which is exactly what you would like. And if I want to make a Bayesian hidden Markov model, I have to uncomment one line and just run it again. So I don't have to rederive anything. And the real attraction of probabilistic programming is I think it could really revolutionize scientific modeling, because that's what, it's very fundamental to scientific modeling to have models and try to figure out what's a good model for data, but also machine learning and AI. And here are just some interesting pointers to useful tools and resources out there. Pyro, this language that we developed in AI labs at Uber, is a really interesting language because it kind of tries to bring together the best of deep learning and the best of universal probabilistic programming. So what we're trying to do here, based on PyTorch as a framework for doing deep learning, is to layer on the ability to express any probabilistic model that you can write down in Python. So the idea of a universal probabilistic program is that anything you can write down in a Turing-complete programming language that calls random number generators is a valid probabilistic model. And that's the class of models that you want to be able to do inference in. So have a look if you're interested in that. And the last thing I want to talk about very briefly is this project that has been a long-going project called the Automatic Statistician. This is sort of an AI for data science, where we're really trying to develop tools that automate aspects of inferring models from data. And here, by data, I mean like tables of numbers and things like that. And not just that, but trying to explain those models in a report, in an interpretable way to the end user. Okay. So I'm going to just skip over some of this. We have time for some questions. But in goes the data. The thing churns over possible models using Bayesian Occam's razor to figure out good models for the data. It comes up with the best model it can find, and then it tries to explain it in a report. So it involves some classical ideas like search, trying to find good models, the stopping criterion there. This is for a time series example. It's getting better and better models, and then it stops using a concept called the marginal likelihood, which simply comes from the sum rule and the product rule. It's not a new concept. But basically, it's a way of trading off the model complexity with the data fit. And MDL criteria can be seen as approximations to the marginal likelihood. And then in the end, when it finds a model, it comes up with an explanation. Here's an executive summary of an explanation generated by the computer program. And here are just some example reports. This is like the first page of a 10 to 15 page report that the system can generate. And if I have some time, maybe I'll show some videos at the end, but I want to leave some time for questions. So let me come back to how to build an AI system. And it's very interesting that nobody, as far as I could tell, nobody thought we have the principles that we need for building AI systems. But I asked people to raise their hands. Because I must be weird. I actually think we do have the principles we need. I think we kind of know how to do it. It's just really computationally intractable. We have the principles that we need. You know, I don't know if you want to call deep learning a principle, but, you know, differentiable nonlinear functions is a good idea, clearly. Optimization is a useful tool. You know, Bayes' rule, Bayesian inference is a general principle for doing perception, and more data is a principle, if you want to call it a principle. More data always helps. For learning, well, there is a one equation that tells you how to do learning from data. At least that's what I believe. We know how to do learning. It's not, okay, sorry, I'll take questions later. I can see, you know, we can use, if you don't like Bayes' rule, at least we could use the likelihood principle. Almost everybody agrees on the likelihood principle. Optimization is also useful. For reasoning, you know, we have logic and probability theory. Do we need more than that? I'm not sure. When we search, you know, these are tools. Decision theory is well developed. We know how to make optimal rational decisions under uncertainty. We have things like Bellman's equation that tell you how to do sequential decision making. We have game theory. I think we have everything we need. Okay, and it's weird that I'm the only one who thinks that. But what we don't have is, you know, we write down the equation for rational behavior, and then we say, oh God, all these integrals and all these sums. Maybe optimization is a way of approximating that. Well, we need better ways of approximating the intractable computations involved. So all this work on amortized inference, Monte Carlo methods, variational methods, recognition models, value functions, these are just ways of approximating optimal behavior. More data, more compute. So I am optimistic about AI. Okay, so to conclude, probabilistic modeling offers a framework for building AI systems that reason about uncertainty and learn from data. And when you combine probability theory, which is about inference, with decision theory, which is about decision making, then you have the foundations for rational decision making systems. And that's it. So I've briefly reviewed some of the things that I think are exciting, and these you can think of as tools on the way to AI, because the problem is computationally intractable, so we need better tools for representing uncertainty in our deep learning methods. We need better tools for doing automated inference over computer programs. And we need better tools for searching for models and explaining them. So the last things here are, there was a review paper I wrote now 3 years ago on basically this topic. Of course, we're hiring. So if you're interested in these things and interested in changing the world through probabilistic modeling, Uber AI Labs is hiring, not just probabilistic modeling, but all other areas of AI as well. And all the work that I did was in collaboration with lots and lots of really smart people. Okay, so thank you very much. I'll take some questions.
Thanks for that really excellent talk. So just going quickly back to Cox's axioms. So one of the things they state is that a robot the order in which a robot incorporates pieces of information shouldn't affect sort of its final belief state. But this isn't really true for humans, right? What we see initially triggers confirmation bias, which affects how we incorporate future information. And you could say that's a bad thing, but
it is a bad thing.
But it's also
terrible. Humans are terrible decision makers.
You could also argue that it's part of how we make these intuitive leaps without getting distracted by unlikely possibilities.
Yeah, okay.
So just if you had a generative model for the emergence of intelligence in the universe, right? It might be true that very few randomly drawn intelligences would actually satisfy the Cox axioms. So I just want you to refute that.
Okay. I'm not interested in biological intelligence. Actually, I think that it's just, you know, we're just lucky apes. We're not some pinnacle of intelligence. We're deeply irrational. We're lousy at doing very simple things like multiplying large numbers. In a few years, I think we'll look back on humans and we'll think, well, we clearly got the idea of intelligence wrong because there are all these systems that are more intelligent than us in many different ways, and the world doesn't revolve around these funny apes, just like, you know, the universe doesn't revolve around planet Earth, which Copernicus kind of helped shed light on. So, sorry if that sounds harsh to all the other human beings in this room, including myself. Let's not get too full of ourselves. If we want a theory for rational behavior, humans might have some good hacks that we could approximate, but we shouldn't aim to mimic humans.
Thanks.
I have a question here which kind of relates to his. I mean, the whole idea of Bayesian learning is based on having a good prior. Now, how can you imagine that you have a good prior for the link edge number 2017 in layer 307 in a deep neural network? And your answer was, it's simpler than you think. I interpret this as simpler as you think, as it doesn't really matter. And if it doesn't really matter, the whole Bayesian reasoning falls down.
No, there are several deep misconceptions in that question. So first of all, the whole Bayesian framework doesn't depend on having a good prior. The point is, it's not that there is an optimal prior or anything like that. Basically, if you want to build a rational decision-making system, it needs to be able to represent the things that may be possible in its world, and then it needs to be rational under those assumptions. You don't need to get the right answer. You just need to cover possibilities. That's why most Bayesians work on things like Bayesian nonparametrics, and even deep learning architectures can be thought of as nonparametric because they have a lot of capacity. They can model lots of different functions. And now, let me follow up with a second question. It's the whole problem with the nuisance parameters in your model, like this weight in the neural network, is that that's not the right level at which you should think about the model. The model is a function from x to y, and actually the priors that we should think about are what are sensible functions from x to y. The representation in terms of parameters is actually just a really big distraction. So that's why when we build systems like, for example, the automatic statistician, we try to ensure that there are sensible priors over functions that we can talk about, which is ultimately the input-output data behavior that matters. So priors should be always grounded in potential data that you could observe. Parameters of a neural network have nothing to, or very weak things to do with potential data.
But I think you're missing the no free lunch theorem. It's a theorem. We cannot do anything without prior knowledge. We can prove it.
Of course, that's the best argument for being Bayesian.
No, because where is the prior knowledge coming from? If the prior knowledge is arbitrary,
from a Bayesian point of view, the only thing you have is data. Unless you make assumptions, you can't make any predictions. And the way you represent assumptions in the Bayesian framework is through probability distributions. You can represent them differently, but you have assumptions as well. So let me move on to, unfortunately, and this sounds crazy, but I have to run to the airport. And it's not because I'm trying to run away from Shai's great questions. I'm going to take two more, and then I'm literally going to run to the airport. Right, actually, I'll take a car. But.
All right. Just a quick question. So I agree that the models and approaches are partly to blame for the lack of uncertainty modeling. But I would also say the validation methods are also partly to blame, because whenever we validate models, we only validate how certain the models are, but we don't really validate how uncertain the models are.
Yeah, no, I agree. I mean, most metrics that are used for evaluating performance do not look at uncertainty. And, you know, I would like that to change, but it's sort of a cultural change. You have to basically say, you know, give me the likelihood on held out data. Don't give me just the error rate. Because maybe in some cases it's really bad if you get things very confidently wrong.
Right, and it's also helpful because humans are very good at uncertainty modeling, so maybe we can have data points which the model should essentially classify as uncertain.
Yeah. Great.
Yes, thank you. It's a very interesting talk. And I wonder, suppose in 50 years the quantum computing has solved MCMC problems, make it tractable, and PyTorch is taught at undergraduate levels. At that point, let's say AI is strong. The problem then might be, what is rational? What is the ethical things we should build into a system? I was wondering if you had any Thoughts on that?
That's a great question. I mean, rational decision making depends on, some representation of what you're trying to decide, right? Some loss function, utility function, and so on. And that's sort of clearly in the realm of ethics, and that's why we need to understand the sort of ethical implications of the sort of things that we try to optimize. So somebody hopefully agrees, at least. That's deeply important, and we should be working on. And it's something, for example, the Leverhulme Centre for the Future of Intelligence is looking at the impacts of AI, both positive and negative, and looking at how to build, good outcomes for the things that we care about.
Okay, I promise I'll be real quick. So thanks for the wonderful talk. I just wanted to get your quick thought on approximate Bayesian computation method, likelihood-free methodology. It seems to be very popular among biologists, but doesn't really get any traction among AI.
ABC is a very interesting method that you referred to. Interestingly, some of the core tools that are used in probabilistic programming are related to ABC. There's a deep connection there. I think that it's one of many tools that can be used for approximate inference. I like to make sure that people don't get too in love with one particular tool, that they empirically evaluate different tools and see what works best. Okay, I'm going to have to go. So thanks.